Welcome back to the deep dive. Today, we are strapping in for a high-velocity tour of the AI frontier.
Absolutely.
We're drawing primarily from the Comprehensive Artificial Intelligence Index Report 2025, and, well, all the adjacent research that really defines the state of play right now.
It's a lot to cover.
It is. So if you want a thorough, structured understanding of where the AI numbers actually sit, not just where the venture capital buzz is, then you are exactly where you need to be.
And I have to say, the velocity of change in these sources this year has been, well, truly mind-bending.
Even for you?
Oh, especially, even for researchers who monitor this space daily. We've seen the old rules of like scaling and compute efficiency just completely shattered.
Right.
Which has in turn fueled this intense, almost desperate geopolitical competition. And at the same time, it's forced this really uncomfortable realization that governance and ethical policy are playing a frantic and currently losing game of catch-up.
That sets the stage perfectly. Our mission for you today is to distill the three colossal shifts defining this era. First, we're going deep into that intense geopolitical race and the massive infrastructure headache it's causing. Think carbon emissions and data scarcity.
A big one.
Second, we'll analyze the radical improvement in model efficiency, reasoning, and the emergence of true multi-step AI agents.
And finally,
we will tackle the critical and, frankly, often ignored issues around safety, the deep-seated biases that persist, and the policy landscape that's just struggling to keep pace.
and the core tension, it really runs through every segment of this dive.
It does. It's this two-speed problem.
Exactly. You have technical capability that is accelerating exponentially, but then the foundational challenges, from energy sustainability and carbon footprint to, ethical governance and data provenance, are scaling up just as quickly.
Yeah.
And understanding that divergence is really the key to understanding the future of AI.
Okay, let's unpack this with a statistic from the index that, honestly, it just forces a fundamental reassessment of everything we thought we knew about AI progress.
I know the one you mean.
For years, the mantra was simple. Bigger models equal better performance. But if you look at the efficiency curve, in 2022, the performance bar was set by models hitting a 60% score on the MMLU benchmark.
And let's pause there quickly just to define MMLU for everyone.
Good idea.
MMLU stands for Massive Multitask Language Understanding. It's a crucial industry benchmark that tests a model's knowledge across 57 different subjects.
Everything from U.S. history to physics.
They're advanced mathematics, yeah. Hitting 60% on MLU was, for time, a real sign of frontier competence.
Right. And the smallest model to achieve that 60% threshold back in 2022 was Palm.
A true behemoth.
A behemoth, exactly. It was clocking in at 540 billion parameters. I mean, it required the resources of a global tech titan to train and deploy.
A huge technological and financial barrier to entry, certainly.
So sure, fast forward just 2 years. It's not a decade, it's 2 years to 2024.
Right.
And our sources point to Microsoft's Phi 3 Mini hitting that exact same 60% MMLU threshold.
But here's the kicker, and this is the part that's just, it's hard to wrap your head around.
It's the parameters.
The parameters. Phi 3 Mini has a mere 3.8 billion.
From 540 billion down to 3.8.
That's where the magnitude hits you. We've witnessed a 142-fold reduction in model size and computational requirement to achieve the same fundamental capability.
In just 24 months.
In just 24 months.
I think we need to stop and really reflect on that number. 142 times less computation, 142 times less memory.
Less financial input needed.
Right, for the same level of intellectual performance. What this metric tells you, beyond anything else, is that the landscape is fundamentally changing.
It's no longer just about brute force scaling.
Not at all. It's about architectural brilliance, optimized data curation, and these efficiency breakthroughs.
And that 142-fold leap is the headline, because it means sophisticated MMLU passing AI is rapidly escaping the exclusive confines of trillion-dollar laboratory.
It's being democratized.
It dramatically lowers the capital barrier to entry, which means capable AI is becoming accessible to smaller tech companies, to university research labs, and potentially even individuals much, much faster than anyone in 2022 would have predicted.
So the era of needing a trillion parameters to be competitive,
It's over.
that democratizing efficiency shift, it immediately plays into the global contest. So let's jump straight into the geopolitical race.
Absolutely. So the index clearly indicates that the U.S. still holds the lead in the sheer quantity of notable model releases.
In volume.
In volume. When we look at institutionally produced models, the ones that are either significant research breakthroughs or immediately commercialized products. U.S.-based institutions produced 40 in 2024.
And how does that compare?
Well, you compare that to China's 15 and Europe's 3. So
Yeah.
in terms of volume and market-ready products, American dominance remains strong, fueled by deep venture capital and a very commercialized research culture.
But that quantity lead, it sort of masks the tectonic shift that's happening in quality.
Huh.
And here's where it gets really interesting. The performance gap between the East and West is rapidly narrowing, or in some crucial cases has almost vanished entirely.
It's true. Historically, if you look at major benchmarks like MMLU, MMMU,
T-modal 1.
right, or math and medieval for coding, the performance differences were mostly double digits favoring the U.S. in 2023.
And by the end of 2024.
That narrative had collapsed. Take the math benchmark, for example. This is crucial for testing complex multi-step logical reasoning, something AI systems traditionally really struggled with.
Sure.
The performance gap between leading U.S. and Chinese models on math shrank from a significant 24.3 percentage points in 2023 to just 1.6 points by the end of 2024.
A 23-point collapse in the performance gap in a single year.
It's monumental.
It is. It signals that Chinese researchers have solved fundamental architectural or training barriers in complex reasoning that, it took Western labs years to achieve.
So we are essentially at parity in some of the hardest-to-crack reasoning fields.
Which has to be terrifying if you are running an R&D department betting on maintaining a lead in model quality.
And we can't forget where China still holds a clear quantitative lead: academic publications and patents. They continue to dominate the raw scientific and intellectual property pipeline.
So while the U.S. industry is producing more immediate frontier commercial models,
China is laying the groundwork in terms of foundational research output. It suggests a sustained strategic focus on AI's long game that may pay dividends later this decade.
and this complexity, it goes beyond just a simple U.S.-China duality, too. The index makes a point of noting that model development is becoming increasingly decentralized.
Right, which is driven largely by that efficiency leap we just talked about.
Yeah.
Exactly. We're seeing notable launches emerging from the Middle East, specifically Saudi Arabia and the UAE.
And Latin America, Southeast Asia.
Yes. The knowledge and the means to create a powerful, nationally specific foundation model are no longer geographically constrained.
It signals a new era, really.
A new era of global, decentralized AI competition, where the battleground shifts from who can build the biggest model to who can build the most culturally relevant and efficient model.
That decentralized competition naturally leads us to the models themselves. It's not just that countries are catching up to the U.S.,
No.
but the best models, regardless of who built them, are clustering together in capability.
We call this frontier parity. The difference between the absolute best AI system and the merely excellent one is becoming negligible.
And this is shown by the chatbot arena leaderboard.
Beautifully illustrated, yeah. Which uses ELO scores, the same system used to rank chess players, to rank models based on head-to-head human preference tests.
So it's a popularity contest. If a model wins against another, its ELO score goes up.
Precisely. And the key finding is this. Last year, the ELO score difference between the top-ranked model and the 10th-ranked model was 11.9%.
Okay.
By early 2025, that gap had shrunk to just 5.4%.
So it's more than halved. That reduction means the competitive advantage that used to justify these multi-billion-dollar R&D budgets is becoming, what, ephemeral?
It is. If your $500 million model is only 5% better than someone else's $50 million model, the economics of performance scaling become very questionable.
And the difference between the top two models?
Even more telling. It shrank from 4.9% to a tiny 0.7%.
Wow.
True frontier parity is here. It's forcing companies to compete on integration and usability, not just raw performance.
Now, achieving this level of global parity, where every major player is within a whisker of state-of-the-art, that requires an incredible, unprecedented investment in compute. And that naturally leads us to the dark underside of this race.
The staggering infrastructure cost and the environmental impact. The sources highlight that the power required to train frontier AI models is doubling annually, leading to rising carbon emissions that are a major strategic concern.
I think we need to give the listener a clear picture of this exponential consumption because the numbers on their own, they don't land without context.
Sure.
Let's start with AlexNet, the pioneering image classification model from 2012. Training that model resulted in about 0.01 tons of CO2, a trivial amount.
Negligible on a global scale. The explosion since then is hard to comprehend. GPT-3 in 2020 emitted 588 tons,
Then GPT-4 in 2023.
hit 5,184
What's
tons.
that?
This is not linear growth. This is a vertical cliff of consumption.
Driven by the need for larger parameter counts and longer, more complex multimodal training schedules.
Exactly.
And the latest example from 2024, Llama 3.1-405B, clocked in at an estimated 8,930 tons of CO2 for training.
And to put that into real-world terms,
The average American emits about 18 tons of carbon per year. So training one large AI model now emits the equivalent of nearly 500 average human annual carbon footprints.
it's the energy equivalent of powering a medium-sized town for a month.
Yeah.
When you look at those numbers, the pace of performance is directly tied to a looming sustainability crisis. It means the race for AGI is also a race for clean energy and access to massive, reliable infrastructure.
Which leads directly to the next huge challenge, the data bottleneck. If we keep training bigger and bigger models, we're going to run out of raw material.
The concern is about the finite supply of high-quality, diverse internet training data becoming depleted.
Right. The well is running dry.
Industry projections suggest we may exhaust the truly novel, high-value text and code data within the next few years. The traditional approach of scaling requires ever larger data sets, and the specter of diminishing returns, the data bottleneck, is a major strategic worry.
So the obvious, elegant solution everyone points to is synthetic data.
Data generated by AI models themselves. But that has historically carried a huge risk of model collapse.
Can you explain what exactly model collapse is and why it's such a fundamental danger?
Sure. Model collapse happens when you feed an AI photocopies of photocopies, essentially.
Okay.
If models are repeatedly trained only on synthetic data, they lose representation of the tails of distributions, the nuances, the unusual cases, the exceptions that make language rich and understanding deep.
So it becomes a blurry, average version of itself.
Exactly. The model begins to hallucinate confidently, generating data that is statistically neat but lacks fidelity and general capability. We saw this across different architectures, including both VAEs for images and, of course, LLMs.
So if replacing real data with synthetic data causes the model to degrade and lose its intellectual edge, how do we solve the scarcity problem?
This is where the newest research offers a massive breakthrough. The findings suggest that the disaster of model collapse does not occur when synthetic data is used strategically.
That's so.
Specifically, when synthetic data is layered on top of or used to augment the existing pool of real data, rather than completely replacing it.
So the real data acts as the anchor, maintaining the model's understanding of the underlying reality.
Exactly.
And the synthetic data just fills in the volume or augments specific gaps.
Precisely. Now, this layering approach doesn't necessarily improve peak performance or reduce the test loss further. You still need that original real data for the critical breakthroughs.
But crucially,
It doesn't result in the degradation associated with collapse. It's a vital stopgap measure. It buys the industry time, stretching the existing stock of real, high-quality data with safe, layered supplements until the next architectural breakthrough arrives.
moving from the logistical struggles of infrastructure and data to the raw smarts, let's talk about how the models themselves are getting radically smarter and more expensive. The biggest technical story is the leap in complex reasoning.
Yeah, this revolves around shifting the paradigm from instant one-step inference to what is being dubbed test-time compute.
Okay.
This is the introduction of new reasoning paradigms, highlighted by releases like OpenAI's o1 and o3 models in 2024. These systems aren't designed to generate an answer instantly. They're engineered to iteratively reason through their outputs, checking their own work.
In a way that truly mimics the deliberation of a highly analytical human.
That's a great way to put it. It's a high-end, dedicated thought process.
And the performance gain is absolutely dramatic, especially in fields like mathematics where complex, provably correct reasoning is everything.
Right. We have the incredible example from the International Mathematical Olympiad, or IMO, qualifying exam.
The data is just staggering.
It is. The O1 model, utilizing this test-time compute, scored a stunning 74.4% on the IMO exam.
Okay, and for comparison.
Yeah, compare that to its immediate predecessor, GPT-4o, which scored 9.3%.
Wait, from 9% to 74%?
Yeah, nearly a 65-point jump in performance on a test designed to challenge the world's brightest young mathematicians.
That just highlights the power of structured, iterative reasoning. The model can spend the time and compute resources to think things through step by step, self-correcting and validating its logic.
Right. The ability to solve provably correct problems, like those in arithmetic, complex planning, and abstract logic, increases dramatically when you allow the model to dedicate significant compute time to the solution process.
It's the difference between a student rushing through a test and a professor meticulously working out a proof.
Exactly.
But that leads to the obvious trade-off, which explains why this power isn't yet mainstream for your everyday chatbot request.
The cost.
The enhanced reasoning of O1 makes it nearly 6 times more expensive to run and 30 times slower than the rapid-fire GPT-4o.
It's a cost-benefit analysis. For solving a multi-million-dollar scientific problem or completing a complex financial audit, 6x the cost and 30x the delay might be acceptable for a 65-point performance jump.
But for drafting a quick email,
It's entirely unnecessary. It's the difference between instant information lookup and deep, costly, high-stakes deliberation.
and despite this massive leap, complex reasoning remains a persistent, critical problem. The index tempered the enthusiasm a bit.
It did. It noted that even with sophisticated mechanisms like chain-of-thought reasoning, LLMs still cannot reliably solve problems for which provably correct logical solutions exist.
Especially on instances larger than those they were trained on.
Exactly. The limits of true human-level problem-solving are still very visible on new, challenging benchmarks. They highlighted humanity's last exam, where the top system scores just 8.80%, and frontier math, where AI systems solve only 2% of the problem.
So they excel at applying learned patterns with deliberation, but they still struggle to devise novel strategies or generalize to entirely new logical systems.
That's the barrier.
Speaking of human-level tasks, the world of AI agent systems that can autonomously perform multi-step tasks is no longer theoretical.
No, AI agents are finally emerging as the new functional frontier.
And they have the benchmarks to prove their capabilities, or lack thereof.
Agent benchmarks are now essential because traditional language benchmarks just saturated so quickly. We saw the launch of several rigorous tests designed specifically for agentic behavior.
Like our bench.
RBench, which evaluates complex multi-day ML research tasks, and GAIA, the General AI Assistance Benchmark, which tests reasoning, web browsing, multimodal use, and tool integration.
The results from REbench, comparing agent performance to human performance, are fascinating. They paint a really nuanced picture.
They do. In short time horizon settings, say, a 2-hour budget-top AI systems are scoring 4 times higher than human experts.
So they're faster, relentless, incredibly efficient on burst tasks.
Right, like writing specialized code kernels or processing rapid data analysis. However, the sources note that when the time budget increases dramatically to 32 hours, human performance surpasses AI, outscoring it 2-to-1.
Interesting. So what does that suggest?
It suggests that while AI agents excel at immediate constrained execution, they still exhibit significant limitations in long-term autonomous planning, adapting goals when faced with unforeseen obstacles, and navigating multi-day, unstructured research problems.
The crucial takeaway there is AI is a better sprinter, but humans are still better marathon runners in research environments.
A great analogy.
And if you look at multimodal agents that operate visually, agents that have to navigate websites, interact with buttons, and interpret images, the limitations are even clearer.
Yes, on the Visual Agent Bench, or VE, which tests agents on complex web navigation and image interaction tasks.
Like finding a specific item on a complex e-commerce site.
Or submitting an image-based form, yeah. The top model, GPT-4o, only achieves an overall success rate of 36.2%.
A 36% success rate on web navigation is a massive limitation. It suggests current AI models are far from ready for direct commercial deployment as reliable, complex agentic tools.
Absolutely. If your virtual assistant is failing 2 out of 3 times to complete a task on the web, it's generating more frustration than productivity.
And that demand for capability is driving a new infrastructure arms race.
It is. Companies like Patronus AI are already building generative simulators, these adaptive simulation environments, which they describe as practice worlds for agents.
So they can learn by doing.
Right. These environments generate tasks, update rules, and evaluate the agent's actions as it learns, addressing the critical need for rich, adaptive reinforcement learning environments necessary to boost that 36% success rate.
Shifting gears slightly, let's talk about 2 areas where the leaps were undeniably successful and immediately impactful: coding and creative generation.
Okay.
Looking at coding proficiency, the data suggests that we are rapidly nearing model saturation on existing tests, which is a big deal for software engineering.
We track this using SWE Bench, which features real software engineering problems derived directly from GitHub issues, requiring the model to autonomously implement multi-file code changes to resolve the bug.
And the numbers.
At the end of 2023, the best-performing model soared a mere 4.4% on the verified benchmark set.
Okay, and by early 2025.
The top model, OpenAI's O3 model, achieved a phenomenal score of 71.7% on that same verified benchmark.
That is a massive jump in functional capability.
It means AI can now autonomously coordinate changes across multiple functions, environments, and even legacy code bases to resolve complex software issues with a high degree of reliability.
So researchers are scrambling to develop far more challenging coding benchmarks.
They have to, like Big Code Bench, where AI still only manages a 35.5% success rate. The old tests are just being rendered obsolete.
And on the creative side, high-quality AI video generators went from an experimental curiosity to a production-ready tool in 2024.
This isn't just animated images. This is complex, high-resolution, consistent video.
We saw several key releases that defined this shift. First, OpenAI's O3,
which moved out of restricted research mode and became publicly accessible in December 2024. It's capable of generating remarkably high-fidelity, coherent 20-second videos up to 1080p resolution.
Meta also unveiled the latest version of MovieGen.
Yeah, and this is a significant step because it includes sound generation integrated with the video and critically instruction-based video editing features.
That's huge for commercial use.
Huge. Their most advanced model can create 16-second videos at 16 frames per second, also at 1080p. The move to integrated sound and post-generation editing is key for commercial viability.
And not to be outdone, Google DeepMind launched VO2.
And they internally benchmarked VO2 against competitors like MovieGen and Sora Turbo, consistently finding that VO2 outperformed them on metrics like physical realism and scene coherence.
And what about user preference?
In user comparisons, videos generated by VO2 were consistently preferred over those produced by competing models, indicating a market-ready level of output.
To achieve that seamless, long-form consistency that video generation demands, avoiding flickering, keeping objects and characters consistent across hundreds of frames, new architectural tricks are being deployed.
Right. The index detailed the introduction of the Spatia model, which was specifically designed to eliminate those visual artifacts.
How does it work?
Spatia uses what they call updatable spatial memory, which is a structure that maintains a persistent memory of scene layouts, object positions, and character features across successive frames.
So it's like a meticulous film director keeping a constantly updated continuity log.
That's a perfect analogy. And this technique, which is loosely inspired by neuroscience, allows for consistent long-form generation. And crucially, Spatia is also highly efficient, achieving 20–30% faster inference than its competitors.
By using sparse, targeted updates.
Exactly. It reduces the overall computational demands while boosting quality.
The technical breakthroughs we just discussed, the advanced reasoning, the agent capabilities, the efficiency jumps, they're rapidly translating into real-world applications across science, medicine, and the economy.
Absolutely.
Let's start with AI accelerating scientific discovery.
This integration of ML into traditional scientific workflows is arguably one of the most exciting shifts, particularly in data-intensive fields where manual processing is either prohibitively slow or physically impossible.
Take connectomics, the endeavor to map neural connections in the brain. Google hit a massive milestone in 2024 by synthetically reconstructing a 1 cubic millimeter section of the human brain at the synaptic level.
The scale of this is hard to fathom. This single sample contained about 57,000 cells, including neurons and glial cells, and a staggering 150 million synapses.
That task is monumental. It is the most detailed map of brain connections ever achieved, and it couldn't be done manually.
Impossible. It required specialized machine learning tools designed from the ground up, like flood-filling networks for automated neuron reconstruction without manual tracing.
And 6CLR.
And 6CLR for accurately identifying specific cell types within the dense tissue. This illustrates AI not just analyzing existing data, but fundamentally helping to generate new complex scientific data sets that were previously impossible to assemble.
Beyond just mapping, the sources also mention a demonstration of an entirely autonomous LLM-powered virtual lab.
Yes, capable of generating meaningful scientific discoveries from scratch. This wasn't just a single model answering questions, it was a structured research ecosystem.
How is it structured?
It was brilliantly organized, like a real computational biology laboratory. It featured a central principal investigator model that acted as the strategic manager, guiding specialized AI scientists in specific disciplines, immunology, computational biology, and machine learning.
This demonstrates a potential blueprint for dramatically accelerating R&D cycles.
Right, with the AI system operating as both the strategic manager and the specialist workforce, capable of iterating hypotheses faster than any human team.
We're seeing similar hybrid approaches in areas that govern our planet, like climate science and physics. The introduction of neural GCM is a fantastic example.
Neural GCM is a hybrid model that combines classic physics-based solvers, the equations that govern atmospheric movement, with machine learning components for weather and climate simulation.
And the big benefit here is computational efficiency.
Massive computational savings. It matches or even exceeds the performance of leading traditional models in short and medium-term forecasts, accurately tracking long-term climate metrics over decades and capturing complex phenomena like the formation of tropical cyclones.
And it does all of this while being much cheaper to run.
Exactly, because the machine learning component optimizes and corrects the slow classical physics calculations.
Let's pivot to medicine, specifically clinical care, where the nuance of AI integration is absolutely critical. We often hear hyperbolic claims about AI outperforming doctors, but the data on integration shows us it's much, much messier.
This is the diagnostic paradox, and it's a critical finding for anyone planning AI deployment. A randomized trial was conducted involving U.S. licensed physicians using GPT-4 assistants for complex clinical vignettes.
Oh, patient cases.
Patient cases, right.
Right.
Physicians who used AI scored only slightly better, 76%, than those without, who scored 74%.
So the improvement was statistically negligible.
Negligible. Yet, when GPT-4 was used entirely alone, stripped of human interaction, it achieved a 92% diagnostic reasoning score.
Wow, that's a 16 percentage point increase over physicians working with the AI.
The intelligence is clearly there, but the workflow integration fails dramatically.
Why?
The analysis suggests several reasons. Automation complacency, so physicians stop double-checking the AI.
Right.
Poor user interface design that doesn't present the AI's complex reasoning transparently, and a lack of optimized interaction methods. And on top of that, there was no clear advantage in time efficiency.
So the challenge isn't the AI's intelligence, but its implementation in a system built for humans.
Exactly.
Another fundamental challenge in medical AI is the sheer data gap.
A huge one. Specialized medical models need high-quality, ethical, clinical data, and they simply don't have the vast ocean of data that general-purpose models scrape from the internet.
And this disparity is staggering.
It is. Consider Gatortron, a large clinical LLM trained specifically on electronic health records. It was trained on 82 billion tokens.
Now contrast that with Llama 3.
A general model, trained on 15 trillion tokens.
Yeah.
That's 182 times more data. This huge disparity limits the ability of specialized medical models to generalize and perform at the frontier levels of their general-purpose counterparts.
Because clinical data is sensitive, heavily siloed, and expensive to curate.
Precisely.
On a positive note, AI is showing real promise in addressing systemic issues in healthcare, particularly around social determinants of health, or SDOH.
Yeah, identifying SDOH factors like socioeconomic status, neighborhood, and physical environment in clinical notes is crucial for equitable care planning.
And the sources highlight that fine-tuned classifiers are now outperforming the big general models.
Yes, models like Flanty5XL are outperforming the ChatGPT family models in accurately identifying these factors. And the reason this targeted approach is so important goes beyond just accuracy.
Okay.
The fine-tuned models also exhibit lower bias and fewer discrepancies when race, ethnicity, or gender descriptors are introduced into the notes.
So that shows that targeted training on specialized, carefully curated data can create a more equitable and useful output.
Than relying on general-purpose LLMs, which often just reproduce the societal biases embedded in their massive training sets.
Finally, let's look at the immediate economic impact and job trends. Adoption is no longer theoretical, it's widespread.
The tipping point has been reached. Our sources indicate that 78% of surveyed organizations reported using AI in at least one function in 2024. And generative AI specifically was adopted by 71% of these organizations.
So this is not a pilot program anymore.
Not at all. It's standard integrated business practice across most large enterprises.
And what's fascinating is the clear productivity equalizing effect the index detailed.
Right. AI isn't necessarily helping high-skill workers exponentially more. It's boosting the baseline performance for everyone else. It's lifting the floor.
We see this clearly in customer support roles.
We do. Low-skill workers saw a significant 34% productivity gain when using AI tools, while high-skill workers saw a gain that was statistically indistinguishable from zero.
And in high-end consulting.
The gains were 42.96% for low-skill workers compared to 16.5% for high-skill workers. AI is boosting those initially starting from a lower baseline.
So it's not just a skill multiplier, it's a leveling tool. This shift, however, means that the skills in demand are changing dramatically. What are the hottest AI job skills companies are urgently hiring for right now?
Well, the demand for skills related to generative AI has skyrocketed year over year. The fastest-growing skill sets are centered on integrating complex systems and making the output reliable.
For instance, job postings requiring knowledge of retrieval augmented generation, or RAG.
A colossal 2,047% increase.
We should briefly explain RAG because that massive percentage tells us it's become fundamental to commercial AI.
It has. RAG is a method that grounds the LLM in external, verifiable knowledge, instead of just pulling an answer from its vast internal training memory.
Which can be wrong or outdated.
Right. The RAG system first searches an up-to-date internal database, retrieves relevant documents, and then instructs the LLM to generate an answer based only on those retrieved facts.
This solves the hallucination problem, which makes Gen AI commercially useful.
Which is exactly why the job demand exploded.
Yeah.
Reliability is currency.
And in addition to that, skills related to multimodal models also saw a 295% increase in job postings.
Which highlights the rapid shift towards systems that handle text, code, images, and video simultaneously.
We've established that the technology is accelerating, converging, and being widely adopted. But the flip side is that responsible AI and governance are struggling mightily to keep pace.
IR.
Let's look at policy first, where the EU has again tried to lead the way.
The EU AI Act is truly a landmark global regulation. It's the first comprehensive attempt to govern AI at scale. It was passed by the European Parliament and uses a distinctly restrictive, risk-based approach.
And what does that risk-based approach entail for listeners who need to understand its impact?
The Act structures regulation around 4 tiers of risk. First, it bans several high-risk systems outright, like social scoring systems and AI designed for human manipulation.
Yep.
Second, it imposes strict requirements on high-risk applications like medical devices and critical infrastructure. Third, it implements clear transparency obligations for systems like deepfakes and chatbots.
And finally, general-purpose generative AI.
Right. It sets minimum transparency and safety requirements. Crucially, its provisions are set to take effect in phases throughout 2025 and 2026, giving the industry time, but not much to comply with this stringent new framework.
Meanwhile, the U.S. government has prioritized national security in its approach, focusing primarily on controlling the inputs.
The hardware and the data that fuel the AI race.
Right. That focus is manifested through 2 main avenues. Firstly, the increased export controls of high-end semiconductor manufacturing equipment to China.
This is a sustained effort to limit China's ability to domestically produce the most advanced semiconductors and circumvent earlier restrictions.
They're targeting the computational engine of the AI race.
Exactly. And secondly, the focus has been on data sovereignty.
Okay.
We've seen executive orders implemented to restrict or ban data transactions involving sensitive U.S. data with countries of concern. This is a direct measure to safeguard critical U.S. data.
Whether it's health, defense, infrastructure.
All of it. To stop it from being used by foreign adversaries to refine their own AI algorithms, it treats data as a strategic national resource.
And as the U.S. focuses on control and the EU focuses on regulation, other nations are signaling massive investment.
Which showcases the truly global competitive nature of this entire technological revolution. Yes, the sources highlight Saudi Arabia's launch of Project Transcendence, a monumental $100 billion AI initiative.
Instantly making them a global investment player.
Absolutely. This includes a major strategic partnership with Alphabet, Google's parent company, involving a planned investment between $5 and $10 billion, specifically for developing sophisticated Arabic language AI models.
That investment isn't just about raw spending. It's about cultural relevance and strategic diversification.
It serves multiple purposes. It aligns with Saudi Arabia's Vision 2030 goal of diversifying its economy away from oil, turning it into a meaningful global AI hub.
But it's also about soft power.
And ensuring that the AI systems used locally are trained on culturally and linguistically specific data, rather than relying solely on Western-centric models.
Next, we have to tackle the inevitable issue of AI-related misinformation. especially regarding election integrity, which dominated headlines in 2024.
Hmm.
Our commitment here, as always, is impartial reporting, just detailing what the sources found about the misuse of this technology.
So in 2024, AI-related election misinformation spread globally with frightening speed. It was found in over a dozen countries and across more than 10 major social media platforms.
And this was during major voting cycles, like the U.S. presidential election.
Right, and we have concrete, verifiable examples of how this technology was deployed in real political campaigns.
In India, for instance.
In India, campaign workers for the incumbent party received personalized videos created using voice cloning and lip-matching software. These videos featured a party member addressing the individual recipient by name, encouraging them to share the party's message.
This personalized scale is a new dimension of political outreach.
It is. And we saw weaponized deepfakes in other regions. In Pakistan, deepfakes emerged the day before general elections, featuring the voice of former Prime Minister Imran Khan and another opposition leader, Yasmin Rashid, both calling for election boycotts. These messages, strategically timed and highly deceptive, aim to depress voter turnout for the opposition.
And in the U.S.,
a Chinese government-linked spamouflage campaign used AI-generated images to exacerbate political polarization ahead of the election, specifically targeting negative posts at political figures and general election integrity.
the goal was clearly to sow discord and cast generalized doubt on the democratic process.
Yeah. But what's important to note, and this is a key finding from the research, is that questions remain about the measurable impacts of these campaigns.
That's a crucial distinction.
Despite widespread expectation that AI-generated misinformation would have a profound immediate effect on election outcomes, the data suggests the actual measured effect on voter behavior is still unclear.
So we saw a lot of noise, but the quantifiable shift in votes might have been less than feared.
Possibly due to audience skepticism, rapid countermeasures by social media platforms, or, frankly, the poor quality of some early deepfakes.
Now, let's dive into a problem that is arguably harder to fix than deepfakes. Deep-seated bias within the models themselves.
This is one of the most troubling aspects of the index. We're looking at research that shows large language models are not neutral mirrors of the internet. They actively train, absorb, and reinforce harmful societal stereotypes derived from their massive training data.
For instance, associating negative terms with Black individuals.
Consistently and disproportionately, yes. And they exhibit clear gender bias, too. The research shows models strongly favor men for high-stakes leadership roles over women, with women being associated more with humanities subjects and lower-status administrative roles rather than high-status STEM fields.
But the most significant and alarming finding here is the concept of scaling bias.
This research demonstrated a counterintuitive truth. Implicit biases, the subtle structural associations, actually increase as models scale up.
Even though decision bias and rejection rates on standard safety benchmarks may decrease.
Exactly.
Wait, if the models get safer on official tests, how can they simultaneously be getting more biased?
It creates an illusion of neutrality. As models become more sophisticated, they learn to superficially pass standardized safety filters.
So they won't directly generate racist or sexist content that triggers an explicit rejection filter?
Right. However, their underlying learned worldview, derived from absorbing the internet's totality, becomes more structurally skewed. The bias is simply pushed deeper into the model's architecture, making it more insidious, harder to audit, and harder to detect.
That difficulty in auditing is compounded by the lack of transparency in the training data itself. If we don't know what went in, we can't fix what comes out.
And an audit showed that over 70% of datasets used for training foundation models lacked adequate license information, posing massive intellectual property and ethical risks.
And of the licenses that were present.
50% were miscategorized. This systemic lack of data transparency creates a massive gray area for commercial deployment and makes public or academic scrutiny of the model's origins virtually impossible.
Finally, let's wrap up this section with the cat-and-mouse game of security and safety research. As agents become more capable and complex, the attack surface expands exponentially.
On the defense side, we saw encouraging research on targeted latent adversarial training, or LAT. This technique is a major leap because it proved highly effective in reducing vulnerability to adversarial attacks.
And even more critically,
It eliminated hard-to-find backdoor vulnerabilities that could be secretly injected during the training process, and it did so even without prior knowledge of the trigger mechanism used to activate the backdoor.
That's a vital defense mechanism, ensuring models cannot be weaponized secretly. But the research points to a major red flag concerning the next generation of AI multi-agent systems.
Absolutely. The warning is that multi-agent systems, or MLLM agents, those interconnected teams of AIs we discussed earlier, are still highly vulnerable to low-resource jailbreaks.
These are basically cheap, easy methods for forcing the agent chain to bypass its internal safety guardrails.
That's right, because the vulnerability in one agent can cascade throughout the entire system.
Their interconnected nature creates compounded failure points.
Exactly. And while theoretical containment strategies exist, ideas on how to stop the agent from running amok, the researchers noted that no practical real-world mitigation measures currently exist.
Which makes the security risk of deploying interconnected multi-agent systems at scale a critical, unaddressed problem for the next 12 to 24 months.
If we take a step back and look at the whole picture provided by the 2025 AI Index, two enormous interconnected themes dominate our findings.
Okay.
First, there is the massive, almost unbelievable progress in technical efficiency. Small models are doing the work of giants. The ELO scores prove we've reached frontier parity globally.
And agentic and multimodal systems are here.
Right? Complex code-fixing AI and seamless video generation. They're emerging rapidly from the labs and into the product sphere.
And the second theme is the staggering urgency of the ethical and infrastructural challenges. The capability gap between what AI can do and how safely, fairly, and sustainably we can deploy it, that gap is widening.
It is.
The closing performance gap between nations is contrasted sharply by the persistent structural bias that, paradoxically, increases as models scale.
Creating that dangerous illusion of neutrality we talked about.
Right. And governance is still chasing a rocket that already left the atmosphere.
This is a complex, high-stakes feedback loop. To achieve parity and continued breakthroughs, developers are relying on increasing compute resources, which dramatically increases carbon emissions and accelerates the sustainability crisis.
And they are using synthetic data layering to avoid running out of training material, temporarily solving the data exhaustion problem. So, if we connect the dots between the cost, the data, and the technical leaps, what does this all mean for the future of AGI development? We are seeing the exponential, unsustainable rise in training compute and carbon emissions, coupled with the reliance on clever, layered synthetic data to avoid data exhaustion.
That combination leads us to a crucial, provocative question that wasn't explicitly answered by the index, but is certainly implied by its data.
Which is?
The question isn't just how smart AI will become, or even when it achieves AGI, but how long we can afford, both financially and environmentally, to train models on this necessary scale before infrastructure and sustainability become the single largest bottleneck to AGI development.
The performance race, fueled by brilliant architecture, has immediately become a resource race, fueled by physical constraints. We may find that the true limiter of artificial intelligence is not the algorithm, but the energy grid, the physical availability of data centers, and the sheer environmental cost of training the next generation of frontier models.
Indeed. It forces you to consider what happens when only the wealthiest nations or the most centralized corporations with guaranteed energy access can pay the necessary price of admission to even attempt to train the next frontier model.
And that has profound implications for global access and innovation.
It does.
A lot to think about and a massive amount of information to digest. We hope this deep dive into the 2025 AI Index gave you the structured, contextualized understanding you needed to navigate the latest developments at the frontier.
Until next time.